I just want to ask you guys about the face-to-face. Our initial plan is face-to-face next week, right? Next week, Monday starts face-to-face. That simply means that we'll conduct all our classes face-to-face at the campus, which means Monday onwards we'll have to go to campus, right? Now the thing is, right now there is an explosion of infections on the Omicron variant of the COVID-19, right? So I just want to ask your opinion, guys. Um, what do you think about it in terms of going back to campus doing face to face? Did your parents have any concern, any say recently?
So far, no.
Um, so far, no,
No, huh?
not yet. Maybe.
Not yet. All right. So Noel also say no, so far none. Yeah. How
Oh, yeah.
about you, Kelvin?
No.
No, huh? So that's a little bit different from G2. G2, a lot of them voice concern. Um,
The COVID spike again, right?
yeah, spike very very high. I think yesterday was a little bit over 1,000
Yeah.
just for Sabah, right? So it's has bring up a lot of concern with students and their guardians, including our management also, right? So in fact, I heard that our management here in Sabah, also in main campus in KL. Hang on, yeah. Had a meeting today. I'm not sure what was discussed or what was and anything was put forward lah. But we have a we will have a meeting here. Sabah will have a meeting tomorrow. Okay, afternoon. So it might affect your practical for tomorrow. Tomorrow we have practical some 12 to 2 again. Oh, I think should be okay. I think the meeting is going to be after our class tomorrow. So so far I have no update yet, but as soon as I get any information, right, I'll let you guys know because it's worrying because the infection rate is going up so fast, so high, very quickly. In three days, I think from hundreds go to thousands, right? So we have to wait and see what the management say. This is related to because we initially planned next week Monday to start face to face. So there's concern about that. All right, so that's all for now. Apparently, some of the students, also the parents, also very concerned. Yeah, some students prefer to go online until this Omicron is resolved lah. Yeah, so just let you guys know lah what's happening. Yeah, so I will update if there's any info. You guys also can keep checking the intranet to see if because if management from KL has something to say about it, they will share with students via the intranet lah, right? But tomorrow after the meeting, if there's anything relevant, then I will share with you guys also lah, concerning the face-to-face next Monday, right? So possible it might be suspended for time being until the number of factions go down a little bit, but not too sure, not sure yet, right? I'll share with you guys later. All right, so any concern from you guys, from your parents or whatever, can share with me lah, right? And I'll try to pass it down to management. Okay, so today we have a new topic. Right. So the new topic that we're going to cover is this ACL concepts or access control list. Okay, so this is a security aspect that you can actually perform on your router. Okay, in our network. Right. So this actually, in addition to the security prevention that we or mitigation that we talked about last week, yeah, under network security concept. So we continue that with ACL. All right. So I can tell you that ACL is basically a packet filtering, tool that you can find in a Cisco router. Right. So we're gonna look at this week, and then next week we continue with the configuration part. Right. So this week we just look at the concepts, and then next week we continue with the configuration. So you can see that our let me just check very quickly. Did I share or not, you guys, the lecture slides? Not sure, so I will share very quickly. Share with you. There's two parts to it. Okay. Yeah. All right, so I've shared two parts of chapter 4, ACL concepts and ACLs for IPv4 configuration. So feel free to download that slide. Okay, so we're going to look at the ACL concept first, and then configuration on week 5, right? So let me just start this. Right, as usual, I will record our session, and if you have any questions, feel free to raise up your hand, right, to get my attention, and you can unmute yourself or type your message here in our WhatsApp. Sorry, not WhatsApp. In our Meet chat here. Okay. Let me start recording our session. All right, so let's look at the topics for these ACL concepts. First of all, we're going to look at what is the purpose for having ACLs. I mentioned before, it's for security reason, right? So it's a packet filtering tools or service that you can find in your Cisco router, right? And the filtering works based on Wildcard Mask. Okay, so we're going to look at a little bit on Wildcard Mask and how do we use Wildcard Mask to filter, right? So we've looked at Wildcard Mask earlier on in the EIGRP, but now can look at it for filtering purpose, lah, right? Okay, so and after that, we look at some guidelines when you create ACL or access control list in your router. Okay, so there are some rules of thumb or best practices or guidelines when as a network administrator, you're going to create ACL. So what are the guidelines available to you? Okay, and then we look at two different type of IPv4 ACLs. First one is standard ACLs and extended ACLs. So we look and compare between the two and which one should you use for certain things. And okay, whether you want to use standard, extended, or both. Right? Okay, so let's look at purpose of ACLs first. So what is an ACL? So in terms of configuration, you can see in the blue color, right? The font that is blue colored, you can see that those are the way you set it up inside your router. So basically type access list and so forth, whether you deny, permit, and then followed by the IP address and the wildcard mask. Okay, right. So basically, ACL is a series of commands. Okay, these commands allow the router to filter packets. Okay, so filter packets means the router has to open up the packet lah, right, to pick inside the packet header, right? And depending on which layer the ACL is implemented, we're gonna look at if layer 3, we look at the packet header. Packet header means we look at the IP address you can find in the packet header, right? If you're going for the ACL that works on layer 4, we're going to look at what kind of protocol is that. Is it a TCP or UDP, right? So that means we can also filter based on the protocol. We don't allow certain protocols, or we don't allow certain protocols. Or in layer 3, we allow certain IP address or range of IP addresses, okay, based on our wildcard mask lah. Wildcard mask, you can see here 000 is an example of wildcard mask that we use for filtering, right? So by default, if you haven't set any ACL, then there's no ACL configured. Means all traffic will be allowed to pass through the router. The moment you apply this ACL command for an interface, so it works based on the interface. So you have to select the interface and basically set the ACL for that particular interface, right? So if you start to, because it's basically not configured by default, if you start configuring ACL on the interface, then the router notice that you have ACL configured for that interface and start to evaluate, right? That means now you have process this filtering process happening at that interface of the router. So any packets that's going to pass through that interface will be filtered to ensure only the packets that is allowed based on the filter will be passed through. What happens if it's not allowed? Then it's just dropped, yeah? It will be dropped, it will be blocked, right? So an ACL works by having a list. So that means you can combine your ACL list, okay? And the combination of this ACL list will then, you can think of it like a filter and then another filter, you know, like a water filter. Maybe you have 4-stage water filter, right? So the first stage filters some certain things, and then second stage, and then third, fourth. So that means ACL also, if you set the ACL, it will be a list, and the router will go through this list sequentially, okay, and applying the access control one ACL after another until all the list is processed. Okay, but if it you can see later on when it goes through the list, sometimes when you find certain ACL, okay, and filtering, it may not proceed after that. May process through the entire list or may stop at a particular ACL in the list depending on what was entered in the ACL, right? So this sequential list is also known as access control entries or ACEs, yeah. ACEs commonly called ACL statements. So this is an ACL statement. Let me just highlight. So this is an ACL statement, right? And this is an entry. It's an entry. You have multiple entries, right? And then that will be your ACL statements, right? So when network traffic passes through the interface that you configured with the ACL, the router will compare the information that it finds, depending again on layer 3 or layer 4, within the packet against each of the entries in sequential order from the top going down, right? Okay, so if to determine if the packet match any one of the entry, okay, or access control entry. And this process going through one ACL after another is called packet filtering. So you've heard about packet filtering before, right? So this is what it is, right? It goes through what is allowed, what is not allowed. Okay. So if it's not allowed, then or doesn't match the filter, then it will be blocked, right? So example, right? So this is not real commands. This is an example what it means, right? How you read later on when you read the ACLs. It's something like this, like you have to read and understand the ACL. So example would be like, let's say we have RSD students all in a class, right? At the end of the class, okay, if we process, let's say there's an access list control for the students in the class, okay, and at the end of the class, let's say as students wanted to leave the class, we process through access list. So let's say first access list says allow all RSD students leave the classroom. Then as the student is leaving the classroom, we also notice, oh, we have a secondary access list, a second entry, because we are going through them sequentially, right? The first list allows, say, the first access list allows all students to leave, right? And then, but we have to complete reading through the list. So the second access list say, the class rep stay back. So it's like a Venn diagram, you know, if you want to find out, okay, out of all the students, which students stay back or filtered. So that means all students except class rep will leave the classroom, right? Or you can do it this way. RSD class rep stay back, and then allow all RSD students leave the classroom. So what's the difference? The difference is if you do this one, right? It process this list allows all students leave the classroom, but all students already process, so they all leave the classroom. By the time, then it will not go to the second one already because you allow all already, right? That means logically, once you allow all RSD students, you don't bother to check any other list because all students already left the classroom. Think about it, very important concept is how you organize your ACL list. So never put access list that works on all as your first entry. If you want to have all, usually you put at the bottom, right? At the bottom, so that it works like this. RSD class rep stay back, right? And then allow all RSD students leave the classroom, right? So this one stay back, and then the remaining one all leave the classroom. You can see there. because this is subset of all the students, there's still other students that need to be processed, right? So it goes to the second entry. Here, since all students already processed, then you don't bother to go do the second entry anymore, right? So think about it, right? If you're later on when you are designing your access list, please remember this concept, because this concept, if you make a mistake, like like for example, an all students filter up here, then if you still have something that to filter down here, then you might make a mistake, because then you all already processed, this one will not be processed anymore. This one only process a few, so still go to check, right? Check the second entry to to see whether it has anything, any filter for the rest of the students, because class rep is a subset of the students, whereas here is all already processed, Okay, so far, following me so far on that aspect?
Yeah.
Okay.
Okay, okay, so yeah, okay, move on. Yeah, anytime you not sure, let me know. All right. Still back on the what is an ACL. We will try to understand what is ACL, right? So it says here, the router require ACLs to identify traffic to do filtering. So basically, by using ACL, you can limit network traffic to increase network performance. Less traffic means better performance. More traffic means congestion, right? So limiting network traffic, for example, what? Let's say in a work environment, right? In a work environment, you want to filter um, any traffic coming from, let's say at work, the boss don't want people to watch YouTube, right? YouTube is streaming video, so it's actually very heavy on bandwidth. So you might want to put in to an ACL to allow only recognize traffic, or to disallow traffic from specifically from YouTube IP address, for example, right? Because because this ACL is actually based on the company policy. What is the policy allowing in or out, right? So if let's say you're filtering based on source, right? Source IP address, then you can do that, right? Okay, so you can use combination of ACLs to control the flow of traffic within your network. This using filtering, you can allow what traffic to go into this network, but not that network. Basically, you're controlling the flow of traffic. Okay, so although we use packet filtering, it's not necessarily means that just because you use ACL, then your network is secure. Okay, this is just part of the tools that you can do to mitigate security concerns, right? So that's why it says provide a basic level of security. At least you can combine this with other security measures, okay, for your network. Okay, we have seen some of the security measures based on the what you can do on switch, right? So this is one of it lah, you can do on the router. Okay, so to have a better security, you combine all the right, the security tools lah. But this alone is not enough. Okay, so at least it provide a basic level of security lah, right? So filter traffic based on traffic type. So this at the layer 4, right, where you can actually because layer 3 you can filter based on the IP address, and it doesn't tell you what is the content, right? What's the content of the packet? It's just tell you where it's from, where its destination is, and you can filter based on the IP address. But you can also go to layer 4, whereby you can then see the type of protocol used. So that is the traffic type. Okay, the traffic type here is basically you can identify what kind of protocol the packet or the the datagram is carrying, right? Or type of traffic it is, whether it's TCP or UDP, then you can filter, right? Right. Screen host to permit. That means this one is from host inside your network, maybe sending out certain information. So you can screen or filter those hosts, whether you want to permit or deny access to certain network services, right? And then because of that, this one flow control and traffic type, you can provide priority, okay, to certain classes of network traffic. Okay, so packet filtering. I mentioned before that the packet filtering, the ACLs work on either layer 3 at the network layer or the layer 4 transport layer, right? So the filter basically compare, right, against the access control list, right? With the incoming or outgoing packets, you can both filter both at the inbound or outbound interface, right? And then if you pass the filter, then you forward. If it's blocked by the filter, then it's discarded. Okay, it's not forwarded. Okay, so this is called packet filtering. Why is it packet filtering? Because you open up the packet, right? Because you open up the packet to look inside. So packet filtering can occur at layer 3 or layer 4. So Cisco routers support two types of ACLs. Standard ACL, this works at layer 3, okay? And it uses source IP version 4 address, okay? So when the router is filtering, it will open up the packet header. It will look at the addresses, but it will only read the source IP version 4 address. Okay, this is standard ACL. If you want more than that, then you have to use what is called extended ACLs. Now, these ACLs filter at layer 3 using the source, not only the source, but source and destination. So if you want to filter destination as well as source, then you have to use extended. Standard only filter source, right? Extended ACL also allow you to filter at layer 4. We know at layer 4 is transport layer. Transport layer, you can choose whether you want to use TCP service or UDP, right? So they will filter, the extended ACL is able to filter at layer 4 to check what kind of traffic it is, TCP or UDP. Okay, and other optional protocol type information for final control. Other protocol means if TCP UDP here, but it can also filter other type of protocol. We'll see later. We'll discuss further. Right. So ACL defines set of rules that give added control for packets that enter inbound interface. That means packets is entering from that interface that's inbound, okay, or packets that exit the router. You know that when your packets is enter inbound, right? Enter, right? And then the router will process. Process means what? Check the routing table and make forwarding decision and forward it through the exit outbound interface. So you can place the filter at the inbound as well as the outbound, right? So you can see here, ACLs can be configured to apply at both inbound and outbound traffic. So that means the inbound interface and outbound interface, right? So just be aware that ACLs is not acting on packets originating from the router itself. So if the packets originate, that means you're at the router and you're doing some, you're pinging or doing some, sending some packets from router, it will not be affected by the ACL. ACL only apply on packets inbound or outbound. Okay, so be aware also, because the packets that's already inside your router will be processed, right? So if you want to filter before the packets enter the router, thereby not processed, then you put the ACL at the inbound interface, right? Because if you put at the outbound, right, sometimes you want to put at outbound, but take note that packets filtered at outbound already processed by the router. So if you want to save the processing, you filter at the inbound, right? Because if you block at the inbound, those packets discarded will not be processed by the router. But if you filter at outbound, all the packets have been routed, have been processed by the router. Okay? Right? So far, okay?
Okay.
Okay.
All right, so we go to the next slide. All right, so when its ACL is applied to an interface, it follows specific operating procedures. Okay, so these are the operational steps when traffic entered a router interface with an inbound standard. So standard is checking the source, okay, source IP address only. Okay, so okay, so here is an example where the packets is blocked at, well, is checked at this inbound interface, right? So the router first open up the IP packet and then retrieve the source IPv4 address. Okay, let's say we get that. Okay, you can see here packet source IP address is this, destination is that. So at the inbound, it has to be processed by the ACL, and because it's standard, then we only retrieve source IPv4 address. Right? So let's say we have a list of ACLs. The router will go through the list sequentially. So it will start at the top of the ACL. And then it will start comparing the source is extracted earlier from the packet, which is this one, okay, against the IPv4 address at each ACE, the entry in a sequential order. So one by one. When a match is made, okay, if we match, the router carries out the instruction of that ACL. So this carry out instruction could be permitting or denying the packet, right? And then after that, it will do one by one through the ACE in the ACL, right? If it match, then the remaining ACE will not be analyzed anymore. That means it stopped there. Okay, if it match, then it stopped there. Exactly what I said earlier on. If you put all, it match all, then the rest will not be analyzed. As long as you still have other range that rest that doesn't match, it will continue through down the list. So if there is no match at all until the end of the ACE in the ACL list, if it doesn't match at all, the packet will be discarded. Why? Even though you don't put any, it means it doesn't match, means you didn't put any ACE in the ACL list that will match that particular source IP address, it will still be discarded. Because hidden means you didn't put in the list, is an implicit deny ACE. This implicit deny ACE, the moment you create ACL, it will be there, even though you don't create. at the bottom, at the last one, there will be an implicit deny ACE. It will automatically be applied to all ACLs, right? So this implicit deny blocks all traffic. So that means in order for some traffic to go through, it must match your ACE before reaching this part, this implicit deny. If it doesn't match any, then no traffic will be allowed, because it doesn't match. So it reached this part, implicit deny block all traffic. So please be aware that is hidden, is implicit, right? Is hidden and not displayed in the configuration because you did not put it. It's by default, it's there. So it's secure by default, right? Well, the moment you activate the ACL by entering a entry, this implicit deny is activated. So if there's no matching ACE that you created, it will drop down to this, and that means all traffic will be blocked. Okay, so you have to remember, if you're creating an ACL, there will at least be one permit statement to allow at least at least range or one particular traffic that can pass through, or else you're basically blocking your router, right? Okay, so example, we want to deny this, we want to permit this, then implicit deny any. So this permit, at least there's a permit here, at least this part, there's a potential to match certain traffic, right? If no match at all, that means you're blocking your inbound port, inbound interface, sorry. Right? Okay, so this part, there will be a packet tracer where you can do in the practical, so you can do to verify local connectivity and test the access control list, right? And then you can remove access control list and repeat your test again. See whether it's blocked or not blocked if you remove. Okay, so now we look at the ACE itself, the ACE, the access control entry. And inside the entry, at the back of the entry, you will see the wildcard mask. So here, we tackle that. We look at the wildcard mask in ACL. So this wildcard mask is the one that is potentially permitting or denying, if you based on the IP address, right? Permitting or denying that particular IP address. Okay, so this is the filter itself, the wildcard mask. Right, so let's understand what is wildcard mask. So when we look at the format, we notice that it looks similar to subnet mask. Okay, subnet mask, recall that it's used for ending process to extract or identify the network address based on the destination IP address, and this is done by the router. Okay, how it match right? That's what that means. Subnet mask is used to extract IP version 4 network address. So you want to match, right? Okay. So in opposite to that, wildcard mask is different. It's when you look at the wildcard mask and you express the wildcard mask in binary. Okay. Whenever you see 1, means match. Whenever you see 0, means not to match, right? Okay, so that's the subnet mask, but the wildcard mask is different, right? Binary 1 is not a match. 0 is a match. So whenever you want, whenever you want the bits in the address to match, you put 0, right? Okay, so it's a 32-bit wildcard mask because we are using 32-bit IP address. So that means we, as a filter, because we want to filter IP address. So if our IP address, IP version 4, is 32-bit, that means our mask will also be 32-bit, right? So bit 0 to match, okay, bit 1 to ignore or to block, okay, to not match, right? So where is this wildcard mask? Is this part, the end part, where you can see here. So what does it mean, 0, 0, 0? To match. Means must match this, must match this, right? This exact match. So basically, all 0 means to match. So must match this, right? If you match this, what should I do? Deny, right? This will say match. So when I have a source address, okay, and it matches this one, all the bits, means it has to be 192.168.90.35. So this basically is source, is an IP address of certain hosts in your network, right? So when we see that IP address, because all zeros here must match. So if we match, we look at what we need to do, means deny. So this packet will be discarded. However, the second one, we proceed to the next one. If it match this, because match, right? Match this, then we allow. So after that, we proceed, because we only a subset of all the possible IP address, right? So we go down here, deny any, means apart from these two, all the rest will be denied. So here, block this. Okay, how to read this? At the inbound, if packet is going inside the router, okay, deny this IP address, allow this IP address, and deny or discard all other IP addresses. Only, that means only allow. When you look at this as a whole, means only this IP address will be packets from this IP address source, yeah, will be allowed to be forwarded, because it's allowed to enter the router for forwarding. Right? So that's how we read this part. All right. So let's have a look at some more example on wildcard mask. Right. So zeros are matched, 1 not matched. Okay. So what happens if our wildcard mask is given as all? So must match all octets. So all the bits. Okay. Let's say last octet. We consider last octet. So all 0, that means all bits must match. Right? What about this one? 0063. So convert 63 to binary, you get this. Right? So it means match only the first two bits. Match the 2 leftmost bits. Ignore the last 6 bits. So anything that match the first 2 bits, right? So the address here, so that means at the last octet, because all 0 must match, but then the next 2 bits must match, the rest ignore, right? So what about this one? 15 is this. So match first all 3 octets and 4 bits, ignore the last 4 bits. So it can be any 4 bits here, doesn't matter. The first 4 bits is the one that must match. What about this one? 248. 248 gives us this. Means the last 2 bits must match. But the first 6 bits can be any bits. What about this one? Must match all 3 octets in front. Ignore the third octet. The 4th octet, the last octet. Means any traffic within this range for source IP is 1 to 254, right? So that means within this range, 0 to 255. So valid IP address 1 to 254 will match, right? Sorry, ignore. Will go through. or deny, depending on what you put in front here, right? And anything will match. Any IP address within this range 255, all ones will be ignored. So any will match. Okay. Okay. The filter is this part. Okay. At least the network address part, if this is /24, at least the first 3 octet must match. It means same network. Any IP address, if /24, any IP address within this network will match this entry, and then depending, you deny or permit. So far, okay or not?
Okay.
Okay. So far, okay.
Yeah, right.
Is there a lot of ways to write this?
Yeah.
There's a 01. Is there a 01, 01, 01?
Yeah, it depends on, okay, the situation like this. If you are the network administrator, you say, I want to allow only that host to be forwarded from that LAN. I only want that computer to be forwarded. Then you fashion your and you use the wildcard mask to filter to match, okay, to match that particular host IP address. And then if you say allow, you put allow. If you say it's different, you say, oh, I only want to block that host. Then that host you match. Then you put deny. Right? Or you say, I want to block the entire, the entire host from that network. Right? So you match the entire like this, 00255 from that particular network address, from that particular subnet. Then if you say block, you put deny. If you say allow, the opposite, right? You put permit. First of all, you need to match. What is it, a specific computer? Because specific IP address, or a range of IP address. You can control where by if it's /24, you control the last octet lah, right? What you want, which range you want, by playing around with match, ignore. Match is 0, ignore is 1. Once it match, right? Once that particular packet match, what do you want to do? Now this is what you decide again, right? You decide whether if it match, you want to deny, or that means you want to block, or you want to allow, access into the router. So permit, right? So you can see in terms of that here, deny or permit, right? So let's look at some example. So ACL 10 needs an ACE that only permit the host with IP version 4 address this. So this is /24, right? So /24 to match specific wildcard concept of all zeros. It's very specific, right? If you say only permits this host, means must match all. This must match. So 0, 0, 0, 0. Remember, if you put any one inside the wildcard one, means it now becomes ignore, means some other address will fall through. If you want exactly one host to match this particular IP, then by putting all zeros means you must match every bit of this address, right? But then you say it's permit, right? So this IP address with this wildcard mask, you put permit in front, right? When the ACE is processed, the wildcard mask will permit only that address, right? Okay. So IP address, this is the IP address. Okay. Wildcard mask, if, oh, here put 0015, for 15 is this, ignore the last 4, only take the 0. So this will be allowed, but not exact match. Why? If I have 192.168.1.2, the 2 will be here, right? 1, 0. So 1, 0 is based on the wildcard mask is ignored. You will only look at the first 4 bits, the last octet. So long as it matches the first 4 bit, means match anything match from, because 001 is 0 in front. So the maximum that you can match is 15. Right? So that's why 15 there. So 1.1 to 15 will yeah, 15 will match. Because after 15, 16, it will go up to here. Is no match already because the 0 here, because that's the wildcard mask. Right? Next example. In this case, says you need an ACE that permits all hosts within this network /24. All hosts means ignore all the last octet lah. Ignore means 1, right? So match, but we want that network 192.168.1/24, right? 3 octets. We want to match all this, so 0, but we say any IP address within this network. So ignore the host part. So the host part must be all 1s, because we want to ignore that, so that any IP address, that means logically it's only 1 to 254 lah. But 1 to 254, the range will be matched, because we ignore. We don't want any specific IP address. So 1 will ignore, right? So we ignore the last octet. So is it 1, 2, 3 allowed lah, or denied lah? Will match lah, right? But it has to be precisely that IP, that network address, because you want to match that particular IP, the 192.168.1. Okay, next example. We need an ACE that permits all hosts within this network. So dot means it's a range like 16, 17, 18, 19 until 31. Right? Any address coming from the range of network between 60, I think the third octet, you can see 16, 17, 18, 19, 20, all the way to 31. We allow the host from there to enter a router. So we ignore, we don't care about the last octet. So last octet will be all 1, ignore. But between 16 to where? 31. 16, 17, all the way to 31. We want to allow only that. The 1 and 2 and 168 must match, so all 0. Right? But the third octet, how do we fashion the bits so that we can only allow between 16 to 31? So again, we have to know how to look at this binary lah. So 15 is 4 1s, right? Like this is 15, right? So if we put 15 here, means we only care about the 4 bits here to match. Must match this, right? Must match this. So if we say we want to filter 16 to 31, we ignore the 4 bits here, right? Okay, so let's see. 16 is here. Okay, and 31 is here. So our wildcard marks is ignore the last 4 bits, right? But must match this. So 16, will 16 match?
Oh, yeah.
Will 16 match? Will 17 match? So
Yeah, sure.
16, yeah, so, 1 until, because we know here 1 must match. 0, 0, 0, 1 must match. So that means here we ignore, right? So whatever value here, so it could be 1, 2, 3 until all 15 here, but that means 1, 0, 0, 0 until 1, 1, 1, 1, 1, 1, 1, which is, and this one is 31. So the range between will match. Okay, since we are 16, start with 16, must match. So must be 1 there. That means here 0, 0 must match, right, with this one. So 0, 0, 0, 0, and 1 must match. So this one will always be, must always be 0, 0, 0, 1. But we ignore this part, right? So it could be 0, 0, 0, 1, 0, 0, 0, 1, which is 17, or 1, 0, 0, 1, 0, which is 18, I think, right? And so on until the maximum is all ones, 1, 1, 1, 1. And here must be matched, right? 0, 0, 0, 1. So 31. Okay, so the thing is, based on that, we see we spend a bit of time to understand how to provide the filter if we just want to have that, right? Okay, so that's why here it says calculating wildcard mask can be challenging, right? And if you want to do it quickly in, say, in a test or exam condition, right? You want to do quickly. How do we do? So one shortcut method, here is the shortcut lah. Just subtract the subnet mask from the 255, 255, 255, 255. Okay, this is a quick way, right? Quick way for you to do rather than working it out just now like that. Yeah, this is better understanding, but it's too slow. So one way is, one shortcut is this way lah. You get 255, 255, and all these are all ones. Okay, subtract the subnet mask of that particular IP address. Means if we are given this IP address, what is subnet mask? You subtract that from 255 or all ones, right? And you get the wildcard mask, right? So example, assume we wanted an ACE in ACL 10 to permit access to all users in this network. /24 subnet mask is 255.255.255.0. So 255.255.255.255 minus 255.255.255.0 leaves you with 00255. So that's your wildcard mask. Okay so far?
Okay.
Okay.
Yeah. All right, so another example. Permit network access for the 14 users, only 14 users in this subnet. Now here, notice that the subnet mask is no longer 255.255.255.0. Based on our understanding of subnetting last time, /28 means what? 24 plus another 4, right? 24 plus another 4. So borrow 4 bits. So the last octet is 1111000, right? So that's your subnet mask. So take 255.255.255.255 minus, right, the subnet mask for this /24. So minus all ones, so 000. Then this one is 1111000 minus 11111111. Leave us is 00001111. 4 ones is 15. Can you see that? Can you guys see that?
Oh yeah.
It's something like very quickly just show here. Oh, can you see? So I'll just take. Okay, so 255.255.255.255 is actually 111111111. This 255 minus what? Minus the network address, which is /28. The subnet mask is, if /28, okay, is 1111111111111111. So borrow 4 bits, right? 28, 24 plus 4, 28. So 11110000. This is /28. Okay, network. So what is our wildcard? So we have 0000000 minus, right? 0000000. Now 1 minus 0 is 1111. So that gives us in decimal 0.0.0.1248. What do you get? 15. So that is our wildcard mask. This is 15. Okay, so based on that, we get this because of the /28. All right. Are you guys following me? Is it okay? Make sure okay, huh? Right. What we're following is, it says shortcut way to get the wildcard mask is 255.255.255, which is this one. Minus the subnet mask of the IP address in at concern, this one. I forget about this first. We look at that, /28. /28 is 24 plus 4 is 28. Subnet mask is this. Then we subtract from this, subtract this, right? We get this. Converting this to decimal, we get this. So, and that is our wildcard mask for this particular situation. So, okay? So far, okay, Kelvin?
Okay.
Noel and Farah?
Oh, okay.
Okay.
Yeah, all right. Okay, so another example is given here, right? So then you work that out for yourself. So you just want to permit only this network, that and that, right? We can summarize the two networks as 192.168.10.0/23. /23 means subnet mask is 255.255. Then 23, right? 8 plus 8 is 16. To get to 23, we need a borrow 1, 2, 3, 4, 5, 6, 7. So so seven ones in the last third octet. So ones, 7 ones, then the rest 0. Subtract. Okay, subtract that from 255, 255, 255, 255. It will give us 0, 0, 1, 255. So then that will be your wildcard mask. Okay. Remember, 10 and 11. And then you see here, the wildcard is, if you see 1 there, is actually 0, 0, 0, 0, 0, 0, 0, 1. Right? So we ignore the last bit. The last bit can be 0 or 1. Okay? That's differentiate us between even and odd, right? The rest must match. Okay? Right. Yeah.
So in the ACL, can we just insert the permit comment on it?
Yeah. Means this is to match. What we are doing here is to match. To match our requirement. Say, oh, we want to match these two. Okay? Then we place the wildcard. Once it match, what do you want to do? Do you want to permit or deny? So if you want to permit, you type here permit. If it match, that match address, IP address, permit or deny. Then you type you write here lah. Okay, you type here permit if you want to permit the match IP address, or deny if you want to deny that match IP address. It's two separate things lah. Here this part is the match. So far the wildcard is for us to have a matching.
Oh.
So this is an ACE, access control entry. Okay, this part is for matching. If the IP address of the inbound, let's say inbound packet has the source address match this filter. After matching, then the router will check this. Is it to permit or deny? Okay, in this case, we want to permit. So we put permit. Is that okay, Noel?
Okay.
Yeah? Right. No, just remember, there is an implicit deny all at the bottom of the list, which you don't see. It's there. Once you activate ACL, it's there. So if your entry, none of your entry will match, then all traffic will be blocked because it's deny any at the bottom, right? Any stands for any IP address, and that's implicit. Whether you enter or not, it will be there. So just remember, as you are creating the list, there's a entry at the bottom where if none of your entry that you entered match any of the IP address, then it will fall down to that default one, which is deny all. That means it will block traffic. Only those matching and permit will be allowed through. Matching, permit. Okay? All right, so Cisco iOS provides 2 keywords to identify the most common use of wildcard masking. The 2 keywords are horse That means you can put in any, meaning match anything lah. That means the mask will be all ones. Ignore lah. That means match any. Ignore all. When the ACL encounter this mask, because it's all ones, that means it's all ignore. Means any IP address also will be matching. Okay. Then instead of writing 25255, you can just type. You can just use any. Right? Or if you want to match a specific, because you have to specific, because must match all. 0000 means must match all bits. It's the same as must match that host address. So you can put host as a keyword. Right? Instead of typing 0000, you can use the host. Later we'll see some example of using these two keywords. Deny any, and the implicit one is basically one example of using any keyword. Right, so let's look at guidelines for ACL creation. Right, so there's a limit of a number of ACLs you can create. Each ACL will have entries inside there, right? So because we have inbound interface and outbound interface, right? So for dual stack routers, where it supports both IP version 4 and IP version 6, a router interface can have up to 4 ACLs applied. Because think about it, one interface here can be both in the context of where the direction of the flow of the packet is. If the packet is entering the router, then this is inbound, considered as inbound interface. If the flow is coming from here to enter the router, is inbound. But what if the packet came in from another interface, processed by the router, now is going to leave the router here? Then that packet is considered outbound. So this interface has, you can set for IP version 4, 2 ACLs, one inbound, one outbound. So 2 already, right? Let's say you support dual stack, which means you support IP version 6 as well as IP version 4. So that means you have inbound and outbound for IP version 4 here. But to support IP version 6, you can also have IP version 6 inbound and outbound ACL. So any particular interface will have 4 ACL as a maximum. So you can see the list here. Is that okay with you guys?
Okay.
Okay.
Yeah. Can understand, if packets coming in here, that consider it will act, if you have an ACL inbound, then those packets coming in here will be checked against the inbound ACL IP version 4. If after processing IP address from coming in from other interface being processed and going to leave this router here, then if you set the outbound IP version 4 ACL, then that packet will be compared against this IP version 4 outbound. If it's IP version 6, then you use this for inbound or this for outbound. So 4. Now, please note that you do not have to configure both inbound and outbound. It's up to you. You want to configure inbound or outbound or both or all 4. Depend on you, the network administrator, to decide what ACL you want to put at this particular interface. Can be 1, can be 2, can be 3, can be all 4. but not necessarily have to put all. Okay, it depends on you lah. You decide. Okay, and usually when you decide, it's based on your organization policy. Okay. Right. So let's look at ACL best practices. Best practices is based on professionals already doing this many times, and then they discover certain things, certain ways of configuring it are the best practice lah. So if you want to know how to configure ACLs, then one of the guideline that you maybe is good for you to follow is the best practices, right? So you must remember you have to be very careful about the ACL. Okay, because if you put the wrong ACL in, means you're blocking traffic, right? You're blocking traffic. Then blocking traffic means downtime for users. You have to troubleshoot, because not necessarily you straight away know it's because of ACL that no traffic is coming through. It could be troubleshoot other things also. Could be your VLAN, could be your STP, could be other things, right? You're doing a lot of configuration, so not necessarily you straight away think of ACLs, but it could be your ACLs, right? So that you will waste some time to do troubleshooting, right? So you have to plan properly. You must have your topology in front of you. You have your organization policies in front of you. Then you design. Okay, where do I want to put my ACL? Inbound, outbound. What do I want to block? What I want to permit, and so forth. Then you can see here the guideline. You must, before you start, you must know first what are your organization security policies, because you will implement your ACL based on your organization security guidelines, right? Then write out what you want ACL to do. Based on this, you design your ACL, right? What is you want ACL to do? Based on the policy, those hosts do you want to permit or deny going into this network, for example, right? Okay, so having a clear-cut documentation will allow you to have a reference, okay? Not only when you first create, but also troubleshooting, right? Okay, so again, as what I already shared with you guys, that you should, you should type out first, and then later on you just copy paste, and because you can basically see in a straightforward your commands. So use a text editor to create, edit, and save all your ACLs. For documentation purpose, you may want to save it somewhere safe as well, right? Again, for purpose of reusability lah, you can reuse your ACLs. Okay, there's a remark command in the iOS will allow you to provide some comments lah, right? So when people go through your ACLs, they look at the configuration, they know what is the purpose, what you're doing, what is ACL, because ACL is basically quite hard to read, especially if you have made multiple ACE, okay, and you're configuring for both inbound, outbound for each interface. You can get lost very quickly without any documentation to tell, okay, I blocked this part, this is one for what purpose or whatever, for compliance to organization, whatever security policy number, section A, B, C, something like that lah, right? You document, so at least people know, okay, you block this part or you permit this one or whatever. There's a reference. Okay, and then when you implement, you better implement it on test development network first, before basically rolling out, okay, rolling it out to the real network. So if there's any problem, if there's any mistake, right, unintended lah, right, then you can debug it first, right? Debug it first, fix it, making sure everything is work fine before you deploy, right? It will help you avoid costly errors. Okay, so these are the best practices lah. But I think you should follow this even when you're doing even if it's not doing on a real network, you're doing on packet tracer. This is a good guideline for you to systematically implement ACL to reduce errors. All right, so let's have a look at the next section, which is types of IP version 4 access control list. So earlier on, we'd say that, and we also looked at example that is focused on standard ACLs, right? Recall that these standard ACLs permit or deny packets based on source IP version 4 address at the header of your packet that you're processing, right? Then we have the second type, which is extended ACLs. So this one, you will try to match the source and destination, and what is the protocol type. Okay, source and destination, TCP or UDP ports as well, and more. Okay, but these are the main parameters you can set for extended ACLs, right? Okay, let's look at numbered ACLs. Just now we say we can put ACL 10, right? So those are numbering. You can put any number you want, right? And the ACLs are numbered between 1 to 99 or 1300 to 1999, and this range are considered standard ACLs, right? While ACLs between 100 to 1999 or 2000 to 2699 are extended ACLs. All right. So it does make a difference. Although you can choose any number after the ACL access list, and then you put number, right? Earlier on we put just 10. So 10 falls under here, this range. So it's a standard ACL. The moment you want to use the extra functionality of extended ACLs, then you must put ACLs within the ID, the number between 100 to 199 or 2000 to 2699. Okay. Right. What about name ACLs? So sometimes for extended, we want to give a name to our ACLs. So it's easier to work with the name ACLs rather than numbered ACLs. So name ACLs are the preferred methods. Okay. So standard and extended ACLs can be named to provide information about the purpose of the ACL, meaning to say the name itself is a documentation of what's the purpose of that ACL. Right? So example, if let's say we want to use extended ACL, we can name it Ftp Filter. Let's say it's for filtering FTP protocol, this file transfer protocol, right? Rather than saying, oh, giving it ACL 100, we give it a name, right? So the IP access list global config command, like this, IP access list extended FTP filter. So we know that FTP filter is extended, right? So once we created FTP filter as an extended, one of the extended, I think it's auto generate, get a number, accepted number from the range for extended ACL. assign it automatically. But you as a human, instead of looking at it as a number, for example 100, you see a more meaningful, okay, more meaningful info here. Instead of like 100, you put you see FTP filter, right? So IP accessory extended FTP filter. So this is FTP under FTP. So for this FTP filter, then you put in the access entry lah, access list entry. So access control entries. Okay, permit, because extended, right? We can specify TCP, the port. Yeah, that means any traffic that is actually TCP traffic. So permit TCP 192.168.10.0, right? Matching to match with wildcard 0000255. What does it mean? It means any address within this network range, I mean network address, right? So you can see any equal FTP. Then we have FTP data. Remember, FTP has two ports, right? Command and data, or console and data for FTP, right? Okay, that's an example. Right, where to place ACLs? Okay, so let's imagine you have this topology. So you're saying, I want to put in ACLs. Right, but let me see. I have this interface for routers. We look at all the interface for routers. This, and this. So where should I put my ACL? Here, 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 here. So let's look at the guideline. Every ACL should be placed where it has the greatest impact on efficiency. Efficiency simply means you don't clog up your network. If possible, you don't. If it's going to, if you're blocking, then you don't want unnecessary processing by the router if it's going to block anyway, right? But might as well block it before and only allow the packet that is allowed entry to be processed by the router, for example, right? That is efficiency. So we have two types, right? Extended and standard. So for extended ACLs, it should be located as close as possible to the source of the traffic to be filtered. Okay, if the source is from this network, these two networks, mean you want to put it there. Why there, not here? Because if here, only traffic from this will be filtered. Rather than put here and here, to here, having the same ACLs, maybe you can put here. But source is here, so you want to block from the source. We don't allow, maybe your policy is, we don't allow any blah, blah, blah from PC1, PC2, right? So near the source being these two networks. Standard ACL should be located as close as possible to the destination as possible. So let's say this is a destination in the context of from here going to here, right? Here's destination. Source should be here. Sorry, standard ACL should be here. Close as possible to the destination. Right? Right, so here are some factors influencing where you should place your ACL. First of all, the extent of your organizational control. That means you as the network administrator, okay, where's the boundary of your network, whereby outside of the boundary you have no access to those routers anymore. Okay. Placement of the ACL can depend on whether or not your organization has control of both source and destination network. Right? Do you have control of the source network? Do you have control of a destination network? Right? The bandwidth of the networks involved. Maybe you're concerned about efficiency or the latency in your network, so you don't want the network to be unnecessarily filled up with unwanted traffic. So if you don't want the unwanted traffic to clog up your network, so you want to put your ACL at the source, because if you filter at the source, then the traffic doesn't have any chance to enter your network to cause any congestion. Thirdly, ease of configuration. It's easier maybe to implement the ACL at the destination, right? Because then you filter traffic. You don't want that it's at the destination. Then you don't have to worry about any traffic, because if you block here, let's say you have further network here, R2 further network. If you block here, you must also have if you block here, what about traffic going out? Not here, not going here, but going here. If you have another here, right, up here, let's say, if you block here the traffic, what if the traffic is not supposed to go to here but go to somewhere else, right? Consideration like that. So if you want to block traffic only going into this, you block here, destination, but the traffic have a chance to go here again, congesting this segment. This is what it says here. It may be easier to implement ACL at the destination, but traffic will use bandwidth unnecessarily until, well, the traffic has to travel until it reaches destination, close to the destination, right? An extended ACL could be used on each router where the traffic originated. This will save bandwidth by filtering the traffic at the source. But then you have to create the same extended ACLs on multiple routers. What it means to say is, here can be the source, here. Here can be the source also, so block here, right? So that means here and here will not be burdened with extra unwanted traffic. But then you have to set both sides, this and this, right? That's what it means. You will require creating extended ACLs on multiple routers. Okay. All right. So here is an example, right? In this topology, the administrator wants to prevent traffic originating from 192.168.10 here, this network, from reaching 168.30 here. We don't want traffic from here to go into here. Here, source, here, destination. We don't want traffic from this segment, this subnet, to reach this subnet. Let's say that's our organization policy. So remember, this is standard. If standard, we block at the near the destination. Have a look back here. As close as possible to destination for standard. So that means here, right? So that's why it says in interface S011 inbound, source is here, and destination is here, to drop. So ACL 10, access list 10, deny 192.10.0, match any IP address from this segment. So 000.255. Deny those, then permit any. If you don't put permit any, you deny, and then the implicit one also deny any. Then no traffic will go inside here. So after you deny specifically this, then permit any. It means from here, any, yeah, right? Only block this one. So to cater for this, this is the access list. Right? Okay, so it says that you can actually put it there and you can put it there. Okay, inbound and outbound. Okay, right? If you inbound, you filter, then it says it will also okay, so R3, okay, R3 interface net, okay. However, it will also filter .10 traffic to the here. Instead of just here, it will block here from here because it denies all traffic from here at here. So it will prevent to go here, but it's also prevent to go here. Can you see that problem? Just now we said we want to block here, right? Correct. We block here means it cannot come here. The traffic from here, we cannot come here. But what if the traffic from here want to go here? Then it's blocked also. So what about here? Much better, right? Because then we block here, but it can still flow here. So that means traffic from here block here, but traffic from here can go here. So instead of here, here is better. Is that okay?
Okay.
Okay.
Okay, let's move on to extended ACL placement example. So the rule of thumb is that extended ACL should be located as close to the source as possible. So if this is our source, this is our destination, close as possible means this router, we consider this router. Okay? But it says a caveat here. If you don't have access to R1, which is the source, then there's no way you can set here because it's not belong to your organization. Let's say this source is not belong to your organization. Then no matter we say, oh, close possible as source, then we can configure R1 because it doesn't belong to our organization. So you can see here, can only place ACL on device they control. Therefore, even though this is the rule of thumb, but we also consider this, right? The context of where organizational control extends. If this is belong to us, then yes. Okay, based on this rule, this. But if it's not belong to us, then we have no choice. As close as possible to the source means if R2 belong to us, then here. If R2 not belong to us, then no choice, right? Okay, so let's look at this example. In this topology, company A wants to deny, this is company A, wants to deny telnet and FTP traffic to company B 192168. This one lah, this destination, right? So we want to specifically deny telnet FTP from here to reach here, right? Okay. So potential here or here, assuming the company A, company B can access company A lah, router. Okay. All right. So okay, it says destination source. Sorry. So it says extended ACL on R3 will accomplish the task, but administrator does not control R3. So company A cannot access R3 to configure. Right? So because we consider first, let's say we don't look at this first. We look at, oh, where possible I can. So R3 also possible, but R3 don't belong to company A. So company A cannot configure this R3 router. Also, you allow the traffic to go all the way through the network to reach there, then you block. Right? We don't want that because that will burden this, congest this network. Right? So R1. Okay. There are two possible interfaces on R1 to apply extended ACL. The first one is here, outbound. Okay, so outbound will process both here and here, traffic both from here, and from this segment, or subnet, here. Or we can here, put ACL here, the G001, the inbound. If you place it here, only packets from this network will be filtered by ACL. Right? So in this case, applying extended ACL to here is the best solution. That is our close to source, and also it only filters this network. Right?
Okay.
All right. Okay, so I believe that is the end of our ACL concept, right? So here you can see what you have learned in this module. Okay, extended to here, very detailed, and here as well, right? Okay, that's just a summary lah. All right, so I'm gonna stop here, stop our recording. So next week we're going to look at the second part, which is the ACL for IP version 4 configuration. That means we will practice the configuration part of the. We're going to look at it lah, not practice. We're going to look at it. How's the configuration? How do we do the configuration of the ACLs? All right. Okay, so let's transfer to our tutorial meet. Okay, I'll see you guys in our tutorial meet.
Okay.
Okay.
Right, so hello, Farah. Sorry, I didn't see your message. Precedence, in terms of priority, I guess, right? In the order of importance. Okay, which one comes first? Right? Okay, precedence. So which one is more priority or importance? So you have a hierarchy lah. Important, the most important first, and then or the most important, and second, and that's it. Macam tu. Kelvin, so I just want to make comment on your answer for part 3, question 1, part 3, yeah?
Yeah.
Yeah. So if you look carefully, hang on, let me just share my screen. If you look carefully at the topology, remember we multi-access where only multi-access network we have the DR and BDR. Okay, which means we have to look at the topology to see whether it's multi-access or single access lah, or point to point. So when we look carefully, between R1, R2, it's point to point, right? Between R1, yeah, R1 and R2 is point to point. R1 to R3 is point to point.
Oh, that one count as point to point also.
Yes, this is a point to point. Remember that the multi-access is the router connects to a switch, switch connects to a router. So those are multi-access, means you can have, so this is considered as point to point, right? Still point to point network. So in this case, there is no,
no need DR.
Yeah.
Oh.
No need DR, BDR. There's no action.
Sorry.
Okay. So only on Ethernet or frame relay kind of network, you will have multi-access networks. So this is considered point to point. Okay, between R1 to R2 point to point, R1 to R3 point to point, R2 to R3 point to point. Okay, so yeah, please adjust your answer.
Oh, okay.
Okay. Right, so part 1, that's correct. In order for precedence means importance. Farrell has mentioned router ID is configured using OSPF router ID. And then second, you look at the highest IP version for address of any loopback. You look for loopback first. Okay, and then finally, then you look at the highest active IPv4 address on the router's physical interfaces. Correct. Right. So part 2, Noel. Right. So router ID is correct. It's because there are 3 active interfaces, no loopback address. Right. So as from our reference from what Farrell has mentioned, if there's no loopback, then the highest active IPv4 will win. So the answer is because of now is highest IPv4 address in any of these physical interfaces is correct. The second one is correct also, router ID for R2, because you have 3 active interface and 2 loopback interfaces. Since you have loopback interfaces, we look at the loopback first. Then from the loopback interface, we look at the highest IPv4 address for loopback interface. Yeah. All right. So now for R3 is also correct. 10.10.10.1. Okay. R3 has 3 active interface and 2 loopback interfaces, but OSPF had chosen the 10.10.10.1 as router ID because we have used router ID command to configure the IP address 10.10.10.1, right? And the IP address 10.10.10.1 does not belong to any of the interface, but we follow the first part of this Farrell's answer. Router ID is configured using OSPF router ID command, right? So the first answer, part 2, is based on physical interface. Second, loopback, and finally on router ID. So for each of the router, we have to evaluate these 3 lah. Okay, based on precedent, you check for this first, and then look back, and then physical interface. It's correct way to answer. State no or yes, sir. So it's no. State whether DR and BDR elected or not elected, so will not be elected, right? And state why, because it's a point-to-point links. Okay. Now, if you want to additional to this is that since you say it's not elected, okay, which kind of network will it where DR and BDR will be elected, right, Kelvin? Which kind of network where DR and BDR will be elected? You can also add additional comments there.
Oh, okay.
Okay. All right, so 2A, correct? 10.1 to 21. Oh, no, not 21. Fairer, it's 10.1.2.1. Okay, the router ID for R1. Be careful of typo. 10.1.2.1. Right? So how did you know that this is the router ID? Using the order of precedence just now, which one did you use to select 10.1.2.1? This is correct, huh? But what did you use to choose that? What is the process that chose 10.1.2.1 as the router ID? Where is it from? Right? Can you add where you get the 10.1.2.1 from? Here. Is it statically entered, or is it look back interface, or is it from physical interface? Okay, so misconfigured. Noel says misconfigured. So let's highlight the misconfiguration. Yeah? That. And that. The two, but there. Right. So what's the correct? The corrected one is this. Right, and this 255 minus 2 slash, what was it? 2
252.
2 by 1 is you get 252, yeah. So this is the correct one. Okay, thing is type there, and also this is incorrect. So this is correct. And router correct. Remove that and then reset it. Okay. The keyword there is no to remove that and then set it back to correct one. Okay, so correct, huh? So Pharaoh said is look back interface. Okay. From the it's true, from the look back interface. Okay. Okay, so it says refer to the network topology in figure 4.4, right? Yeah, let's see, where's 4.1? Three one. 4.1. 4.3.1. Oh, this 5.1. 6.1. Did I miss any? Let me just check. I think there's no 4.1. I think this one, right? The 3.2 is the 4.1. Because it says refer to the network topology. Oh, 3.1. Okay, 3.1, not 4.1. 3.1. This one is from this one, 3.2. Figure to provide two reasons why it is recommended to set interface G00, this one, on R1 to passive. This is passive, right? So where does it lead to? It leads to host, right? So set the G00 to passive interface. So I think it's 3.2. So I just made adjust was 3.2. Right? Do not have OSPF connected. So okay, so correct. Okay, correct. Prevent information routing message through, but still allow the network to be advertised to other routers.
Oh, is there another reason? Yeah.
Yes, I think this one is correct, but it's related to here, and it's this one is related to bandwidth concern. Okay, reduce band congestion. Okay, what should we say? How do we say? Prevent unnecessary traffic, right? Okay, so we prevent unnecessary traffic to go to the host, since the host is not routed, so we shouldn't send the OSPF. So prevent transmission, yes, correct, and still allow network to be advertised, yes, correct. But this is actually related lah. Right? So sorry, these two are related. So the other one is, excuse me. So I just give you the answer. Right? So we are worried in terms of security. Why? Because remember, whenever we have like election or a way for the routing table to be changed based on because it's automated, right? Based on election, things like that. There's a potential that the attacker can influence this, right? So if we allow routing information to be forwarded via that interface, right? So here, right? That means it can send, it can receive, which means if this PC1 is taken over by an attacker and he installed software that can generate fake OSPF messages, right? So he can be sending out fake OSPF messages to R1, which going to influence R1 lah. In this case, of course, there's no multi-access, right? So it's point to point, right? But still, we try for best practice. We try not to allow, just in case next time you suddenly change your topology to multi-access and then election will happen, then PC1 can send rogue OSPF messages to here. So if you block here, there's no messages and the interface is not expecting any OSPF messages being shared. All right, because it's passive already. So that's the security part lah, to provide security for the OSPF routing process by preventing any rogue device from injecting false or less than optimal routing info. Okay, right? Obviously, here is a point to point. So OSPF for point to point, basically, it's just they will exchange here lah. They will exchange, but we never know that suddenly with our topology change, we want to it becomes multi-access, then a rogue device can influence that DRVR election. And then if they influence that they are the DR, then all the routers here will be waiting for the routing table information to be shared. Then if the rogue device are taken over by a hacker, suddenly now start sending wrong routing table, can influence that the path. They can change the path lah, the path where packets can flow. Right? Is that okay, Kelvin?
Okay.
Yeah. All right, challenges for multi-access networks can create two challenges for SPF regarding the flooding of LSAs. What are these challenges? Challenges for SPF regarding flooding LSAs are creation of multiple adjacencies, creating every router is unnecessary and advisable. This led to excessive number. Yes, correct. What we want, what we don't want is, too many sharing of the duplicate information is actually taking up the bandwidth, taking up a lot of bandwidth. We can have a potential that we can have full mesh network created. Full mesh means every other router is connected to every other router and they're all sharing information to each other, right? Right, so extensive flooding of LSAs. The LSAs is the one that the link state they want to share. Okay, flooding because when every time OSPF is initialized or when there's a change in topology, right? They start to reconfigure, converge, right? So they start to flood again with LSAs. Now this flooding can become excessive, especially if you have a often occurrence of OSPF being initialized or change in topology. Can be a source of an attack, right? So the answer is correct. Look for in a multi-area environment, it's normal that the link state update overhead is high. And the SPF calculation runs frequently across all the routers running open shortest path. First, justify your answer. All right. Is it true? Is it correct? In a multi-area environment, is it normal that link state update overhead is high? And the SPF calculation is run frequently across routers using open shortest path first. Okay, so Noel says yes. Okay, your answer, this part is correct, but we are talking about well, actually, in if you have this, right, means it should be. Right, so it depends lah, right? But if you're single, this is you're talking about single area here. No, single area. This is true if it's small single area, but if it's a large single area, then yes, it can go. Overhead could be high, right? But in a context of multi-area, do you think it's still overhead is high?
Mm,
What's the purpose to have multi-area in OSPF multi-area?
to group the SPF
To what? Sorry. To
to group.
group. Okay, but why do you want to group usually? Is it better to have a, let's say you have a large network? Is it better to have a single area large network or divide it into smaller multi-area? Remember, you start off, let's say even if you start off with a small network, single area, eventually you are going to expand. Let's say you are scaling up your network. So do you just expand and expand and expand your single area, or you have single area and then you create another single area beside another single area beside, it becomes a multi-area. But why? Which one do you think is better? One large single area or multi-area, smaller area for multi-area?
Smaller.
Smaller, huh? So that's why multi-area environment is suitable for a larger network rather than large single area. So in this context, is multi-area environments, is it normal that the link state update overhead is high and SPF calculation run frequently across all routers within the multi-area environment? What do you think? See, this one is quite eliminating. Run frequently across all routers running the OSPF. Does it really happen for multi-area?
Does the SPF means sender policy framework?
Yeah, so that means if the thing is topological changes that causes this recalculation and link state update. Link state update is also happen when DR go down and then re-election happen again. So, but it is actually limited to the area where the router is. So a topology change in a certain area, which is part of a multi-area, is localized or limited to that single area, although it's part of the multi-area. So it doesn't affect the topological change or whatever causes that recalculation doesn't go beyond that area. So other areas in the multi-area environment will not be affected. So there shouldn't be a high overhead on that, and it's not going to be across all the routers. It's limited or localized to a single OSPF area. And that is why multi-area, when you're scaling your network to be very large, is no longer efficient to have a single area OSPF. Okay, you start to need to divide your single area OSPF to become multi-area OSPF, so that this is the thing lah. We don't want the this kind of this thing that happening happen all over the multi-area. I mean the single area. If you already divide into multi-area, it will be limited to the particular area where it needs to update the routing table, right? So the sharing of information is limited to localized lah. They say it's localized within an area. So other areas within the multi-area is not affected. So you can imagine when the large OSPF area is divided to smaller areas or multi-area, that means the smaller area will have fewer routers. Fewer routers means even in that smaller area within the multi-area, will be less traffic. Okay, so the key thing here is that LSA flooding is stopped at the area boundary. Okay, it's localized within a specific area.
Is it correct?
Because there's yeah. It's okay. I give you. Yeah, it's correct. I give you the complete answer lah.
Okay.
Okay, the suggested answer lah. Okay. So first of all, say yeah, no, disagree is no, correct. Boleh juga. So in a multi-area environment, it's not normal, it's abnormal. The link state update. Okay, so you mentioned that. In a large OSPF area is divided into smaller areas or multi-area, the link state update overhead and SPF should be low due to less routers per area. Multi-area SPF is useful in larger network deployments to reduce processing and memory overhead per individual router because there are fewer router exchanging LSAs. Okay, localize the impact of a topology change within an area. Right. For instance, a minimized routing object impact because LSA flooding stops at the area boundary. Right. So better, okay, when you write, if you mean an area within a multi-area, it's better not to say a single OSPF area. I think so, because it may confuse between multi-area, single area, kan? So you perhaps can just say within an OSPF area. Gitu. So an OSPF area is already meant one only, kan? Because you are talking about that single area within the multi-area. Case we reserve the single OSPF, single area OSPF as a keyword lah. Is that okay, Noah?
Okay.
Right. Just have to look at how to answer this. Okay. All right, I will continue to mark this. I just noticed that it's already 4 o'clock, so I don't want to keep you guys. It's been 3 hours already. So I will continue to mark this tutorial. I will also start to upload the third tutorial for you. Right, so thank you very much for today, everyone.
Okay, thanks, sir.
Okay, sir. Thank you.
All right. See you tomorrow.